And then we come to the next speaker. That's Vertovec from the University of Oxford about fault tolerant control methods, right?
Yeah, generally speaking, so I'll be talking about generally sort of how we can be enforcing safety, or how I think we should be enforcing safety within the control design for airborne wind energy systems. Yeah, so as I mentioned, I'll be talking about enforcing safety in airborne wind energy systems, and I know that we're not all control people here, so I'll try to keep it sort of more high level and have the sort of take-home message be the general methodology of how I think we should be enforcing safety moving forward within airborne wind. So what we've seen so far within the airborne wind energy sector is that we've successfully have hours or even days of continuous flight. It's automated flight. But most of the time, in order to ensure safety, what we do is we have somebody with a controller on the side ready to take over the kite if something happens to go wrong. And of course, if we want to get to autonomous continuous operations lasting months or even years, we're going to need to start bringing safety more into our actual control design. And we need to do that and also figure out how we want to balance conservatism and safety on the one hand, but also power generation and continuous flight on the other hand. We can't be bringing down the kite every time we have suboptimal wind conditions, but we also can't be flying conservative flight trajectories, etc., and thus sort of compromise on power generation. So to date, most of the sort of the control design that we've seen in the airborne wind energy literature, most of it has been focusing on performance optimization, follows your sort of classic feedback loop, where we have our controller taking measurements and determining control input, and then just simply applying that to a plant. And as soon as we start trying to bake in safety into this and safety constraints, we can do this either by means of, say, using MPC or something, but then we run into the problem that it quickly becomes quite computationally challenging to do this in real time. And so what I would like to propose is that we actually start adopting safety filters. And so safety filters have been around within control theory for a while now, and what they essentially do, they take the inputs of a nominal controller and you run them through the safety filter, and the safety filter is going to determine independently if applying this control input to your kite or your winch or whatever is going to lead to unsafe sort of behavior either now or sort of in the future. And so the way that this has already been implemented within airborne wind energy, which I presented last year at the Airborne Wind Energy Conference, is by means of a sort of a hybrid control setup, where we have our power optimal controller. This can be a controller, in this case I use the NDI controller developed by Sebastian Trapp in Roland Schmier's group. And then we have a safety critical controller, which in this case I've developed using reachability analysis. And then we can use a sort of like this hybrid control setup, so we design it as a switch system, and whenever the safety filter detects that potentially we're going to, in this case, have tether rupture, then we switch over to the safety critical controller. Of course, when we have these sort of switch systems, we have all of the complexity and the challenges that switch systems provide. So in this case, we have to use a mixture of sliding modes and hysteresis switching in order to sort of get that safe switching there. But if we could sort of consider the 3 degrees of freedom model here, where we are essentially designing our safety critical controller in terms of the path following loop, so looking at the angle of attack and the bank angle as our control inputs, and then trying to minimize the tether force, sorry, not minimize the tether force, make sure that the tether force stays below a sort of a maximum tether force. Then what we see in practice is that really only in very, very, very small instances do we actually need to be switching over to the safety controller, and for most of the time we can actually just be using our power optimal controller. And so if we were using a controller that is always trying to enforce safety at all times, we would have a significantly more conservative trajectory that would be flying there. And so what we can see is that throughout flight we're able to maintain really, really, really high tether forces without ever actually leading to a rupture. But can we do better than this? Well, in certain situations, yes, we can. And for that, I'll be looking at the winch controller now. The winch controller, we're going to start by decoupling it from our flight controller. So we still have this elongation term here that has the coupling, but if we assume that we can estimate that elongation term separately, then what we can do in order to ensure safety is we can go ahead and we can define our safe set over our state X here, which X in this case is going to be the bundled up states of our winch. And then we can define our control barrier function here, H, such that whenever H is greater than 0, we consider our system sort of to be safe. And whenever it's smaller than 0, it's unsafe. So sort of a simple control barrier function, if you will, is simply looking at the difference between the maximum tether force and the current tether force, or in this case, in order to account for actuation delays, we look over a time horizon, and we take the minimum over our time horizon. We can then go ahead, because we want to do this all in real time, we want to be able to get this predictive term here to be quite efficient to compute, so we're just going to try using a first order approximation of this. We have tried more complex stuff. We have looked at safety, sort of predictive safety filters, etc. But it turns out, in practice, this works quite well, and I'm happy to chat to the control people more during lunch and stuff about what the different stuff that we've tried out. But I always think if we can keep it simple, let's keep it simple. Now we need to make sure that this safe set here is invariant. So this means that whenever we sort of reach the boundary of our safe set, there exists a control input such that we can drive ourselves back into our safe set. For those of you who are in control, this is fairly standard within the control barrier function literature to sort of define this safety set like this using this gamma term, which effectively just means that the further we are within our safe set, the less we have to worry about this boundary condition. Now, because of the nature of the winch dynamics here, and then being control affine, we can go ahead and we can bundle up all of this yellow stuff here to f of x, and all of this red stuff here to d of x. And then we can simply look at the control input here, u, and then if this control input u will satisfy this equation, then that control input u is determined to be safe. So if we now start off with our original control input u0 that we get from our primary controller, there's lots of nice different winch controllers out there, and we just take that as our sort of our input, then what we're interested in is what is the minimum change that we need to do to that control input in order to make it safe. Most of the time, it's going to be no changes. We can just go ahead and apply that straight away, and then it really does kind of work like a filter, and it lets that control input go right through. But in some situations, it does need to make a small change to that control input. In this case, the control input is the sort of the torque that we provide to our winch. And if we go ahead and we look at the sort of the safety properties of the winch using our sort of our baseline controller. So for the winch dynamics here, I used the megawatt version. I did implement a velocity tracking winch controller instead of the existing force tracking winch controller, which was left over from Sebastian's RAPS work. And we can see that, so the green, I don't know if you can see this at the back, but there's a green line here that tells us this is sort of the maximum allowed tether force that we want. And we sadly exceed that maximum tether force. So this would mean that in practice we have quite a lot of ruptures that we would be encountering. However, when we go ahead and run this through our safety filter, we can see that the results are really quite nice. And we're getting sort of very, very, very smooth behavior. This wonkiness bit here at the beginning, take that with a grain of salt. There are a couple of complications in the dynamics of the winch that we're going to be smoothing out and everything. And so when you sort of go into your traction phase, you need to yank on the tether in order to sort of get your system going. And we've had some problems with that. So don't worry too much about this thing here. This has since been solved. I've been working together with Jesse Hummel, who's a master student from Wall and Schmiel, who's been doing some fantastic work on the winch controller there, which I think is going to probably be published in his master thesis as well. So yeah, the take-home message here. Safety filters are a really, really nice design tool to use in order to add safety to an existing control structure. And I think if we look at the control literature in airborne wind energy over the last 10 years, really the majority has been focusing on performance optimization. And only now are we trying to figure out, okay, how do we now integrate safety into existing architectures? And if we look at all the fantastic work that has been done on really complex safety controllers using MPC, etc., we're not really seeing them being adopted in the industry. And I think we have to often try to stay away from the super fancy techniques and keep it simple where we can in order for it to get adopted in industry and to move everything forward. And so I think if we can show that a really simple control barrier function, like the one that I demonstrated, performs really well, then let's use that simple control barrier function and let's add it into our existing control architectures. So not only does it simplify that design process, but it also allows us to do other stuff with our controllers that we previously maybe didn't want to do, such as, for instance, using learning-based controllers. One of the challenges of using learning-based control strategies is that we have a lot of uncertainty in the input-output behavior, and we don't necessarily know as we're training it and as we're exploring the state space if it's suddenly going to do wacky stuff. And if we wrap this all in a nice sort of safe cradle using safety filters, then we can open up a whole new area of control to airborne wind energy while ensuring safety and while allowing us to go ahead and actually test it in practice. And so this is the sort of the high-level take-home messages. Let's incorporate safety. Let's not always put it in the side because to the side it's going to become challenging later on. And let's incorporate it using these sort of safety filters. So yeah, thank you very much, and thank you for
Thank you, Nikolaus, for these interesting presentations. Are there questions? Yeah, here.
Hi, nice presentation. So just a question about the invariance. So you have that invariance condition. You are not imposing it all the time. It's just to know that the set is invariant, and whether it is a good idea just to impose it when you are near the border. So you have that set h of x less than or equal to 0. So we don't need to impose the invariance in those sets, just when you are near the boundary. And whether we impose that condition in real time, or it's just a condition that it's nice to know that it is invariant, but you don't need to impose it.
Well, it is sort of important to impose it at all times, because what it ensures is that we're not only safe now, but we're also going to be safe in the future, and that we're not, with our control input that we're applying to the system, we're not walking into areas that we potentially can't get out of later on. You can, depending on your application, you can tune this gamma term in order to really make sure, effectively, that when you're very far within the set, it's effectively negligible. And so in this work, we use the gamma factor of like 2, which is higher than average, and so we're really only enforcing it towards the boundary. But the way that it's implemented, so it's a quadratic program, it works really fast, because most of the time it just checks the existing solution and says, yep, that's fine, move on. And so it's only, that constraint is only going to get violated when we're effectively at the boundary, if that makes sense.
Thank you for the presentation. Yeah, I guess you have two kind of controller, one the kite and one for the winch. So my question is that, are you using some feedback from the kite to the winch controller? And if yes, are you considering the communication delay in that?
Yes, so we are assuming some communication delay. There is also, so this work at the moment, I have that elongation term. I think moving forward, that's not the best term to use, and we should try to find an alternative, because that's something that, if we're measuring it in practice, there's going to be quite a lot of uncertainty. So this is more of a proof of concept, if you will. I think more work needs to be done, and I'll be doing more work on that to find models that work better. Concerning the flight control structure, so these were two different types of safety filters that we can see in practice. I think it would be really nice to also design a control barrier function that would work with the flight controller, so that we're not having these problems of a switch system, but that we can use that sort of smooth quadratic program. But there's quite a lot of challenges that go with it. So it has a higher relative degree, so we need to use higher order control barrier functions. The flight control dynamics aren't necessarily controller-fine, so that creates whole own problems. So there's quite a lot of sort of room there for improvement. So I know that you're sort of working at kite mill, I wouldn't recommend using exactly this control barrier function just yet, but more of the sort of the paradigm of using safety filters, if that makes sense.
Thank you very much again, Nikolaus.